Hi everybody, this is Tom Cherryholmes with the next video in the Amiga PAC-MAN series. In this video, we're going to talk about implementing PAC-MAN as what is known in the GEL subsystem as a SimpleSprite. The SimpleSprite system allows direct access to the 8 Amiga hardware sprites that are part of the system as directly and straightforwardly as possible. And ultimately what we're going to be making is this. A program that goes through, actually this is the one we're going to be working on here. If you would like to follow along, there's a copy of it on the GitHub. If we go into my workspace where I'm actually working on this, let's go ahead and open it up and see what we're going to be making. Sprite Pack. We're going to be animating PAC-MAN across the screen right here. Quite nice. And then it's going to sit here for a moment, and then it's going to close the window. As soon as it decides it wants to. All right, there we go. Now, I'm going to show you something rather unusual. A couple things about sprites. First and foremost, you'll notice right here, we have a mouse pointer on the screen here. It's used by intuition, and this is actually Sprite 0 in the hardware in the system. It's implemented as a simple sprite. You'll also notice that the colors of this mouse pointer here don't correspond to any of the colors here on the play field that comprise the workbench. That's because sprites have their own color palette, and in point of fact, sprites can be either 4 or 16 colors. And if they are 4 colors, each of those 4 colors is paired with 2 sprites each across 8 sprites. What this means for us ultimately is that we can use sprites for PAC-MAN in 3 of the ghosts, but we're going to have to implement one of those ghosts as a blitter object, which is the reason for the next video in the series. But we'll get to that soon enough. SimpleSprites are actually handled quite well by the operating system here. If you were to take and deal with these sprites directly using the hardware registers, you would find that the sprites actually exist on a layer above the playfield, and you can move them above the playfield without disturbing any of the elements, the graphical elements below. The system doesn't have to take and redraw them, and this is a very powerful feature. So if you have something that is less than, and the other major thing is that sprites have a constraint of being 16 pixels across. They can be as tall as the screen themselves. They can be as large as the screen, but they are 16 pixels across. And it has to do with how they're actually implemented inside the Denise themselves. But sorry, I digress. The main thing is that you'll notice that the mouse here is smoothly moving across the screen, and it has its own color palette. Same thing is also true with Sprite Pack here. And if you were to take and manipulate these hardware registers directly, you would find that if you moved the elements here, the sprites will stay above the screen, and they would potentially bleed into other screens as you use them. For the mouse pointer, this definitely makes sense, but this wouldn't be desirable for our graphic objects. Thankfully, the SimpleSprite system provides a way when it is moving sprites through the system using the copper list, using the coprocessor, which does all of the screen mode setting and the palette setting and everything, to also affect the sprite position, so that as the sprite is drawn across the screen, its position is adjusted relative to the top of the screen. But we'll see, the moment that this stops, the overlaid nature of the sprite becomes evident. And this will disappear once this window disappears, but you'll see it's rendering itself above all of the other graphic elements. That's just the nature of how sprites work. So with that, the one thing I will say that will be different from the version that's currently up on GitHub, I may change this, is that I'm basing this code on the draw maze code So we're actually going to be starting from a point where it draws the maze, and then we're going to take and draw the sprites on top of it. So we can take and really drive this whole point across, sure. Just to show that it's actually doing its thing, it's overlaying atop all the playfield graphics, and everything's working as it should. So with that, now that I've done a basic explanation of what I'm going to be doing here, let's actually get started implementing Sprite Pack. We come into our copy of Emacs here, and we see our code, which is based on our maze drawing code here. All sorts of stuff happening here. We've got maze borders and everything else. We need to add one include called Sprites.h, which is in the graphics directory. This is important because it's not Sprites.h, it's Sprite.h. This implements all of the function headers and data structures that are needed for the SimpleSprite subsystem. This will have all the bits and pieces that we need so that we can get a sprite, so that we can change the sprite, so we can move the sprite, and so on. Give me just a moment here to take and get my bearings, and we can actually start doing the next bits and the next thing that we need to do. And I think the first thing that we really should be doing is we should be implementing the sprite bitmaps. If you take a look, you'll find in Chapter 3 of the Libraries and Devices part of the ROM kernel manual, the section on animation. You'll see the basic overview talking about the gels, all the different components that we've gone over before. Simple, and the one that we're going to be dealing with here is simple hardware sprites, which is actually covered first. It talks about how the simple hardware sprites work. And if we actually take and go down here to using simple hardware sprites, we get an idea of the functions that we need to use in order to actually implement these things. We need to use GetSprite first and foremost to inform the operating system that we're going to be using a particular hardware sprite for our purposes so that it can't allocate it for another program. We need to use ChangeSprite to modify the sprite's appearance for the different animation frames inside of PAC-MAN. And we need to use MoveSprite to take and move PAC-MAN across the screen, along with the ChangeSprite happening in parallel. When we're done with the sprite, we can tell the operating system that we're done with the sprite by using freesprite. You also have the ability to take and turn on and off sprite DMA so that you can take and gain, or you can gain DMA cycles when you're not needing to use sprites, but in our case it doesn't really matter here, so we'll just take and forget about it. Now, we'll come back to this right here. This is GetSprite, and we're actually going to be using that to, again, allocate the sprite that we're going to get. And it tells us right here with each set of sprite pair that we get. Remember, these 4 color sprites are assigned in pairs to these color registers. So 0 and 1 use color registers 16 to 19, 20 to 23, 24 to 27, 28 to 31. It's worth noting that color register 16, color register 20, 24, and 28 are, by definition, transparent. So you don't get 4 colors, you actually get 3 with a 4-color sprite, because one of those colors has to be transparent. Now, it also talks, very importantly, that these color registers are shared with the color registers that are used to draw the playfield. So if you have a 32 color display, the bottom 16 colors of your 32 color palette will be shared between the playfield and the sprites. This is very important. So we need to take and start by building a simple sprite definition. Now that we've got the headers in, we can start building a simple sprite definition for our PAC-MAN character. So let's come down here a little bit. We'll come down past all of the window decorations, everything here, custom screens, etc. We need to add one thing to our custom screen. And that is that we need to set a flag to tell the copper list that we're going to be using sprites. This allocates the appropriate DMA timing so that sprite pointer fetches can happen. This is important. You don't do this, you don't see the sprites, no matter how hard you try. So let's go ahead, continue down a little bit more. Let's get past the text attributes and color tables and stuff and all of that nifty stuff right here. You can see, again, we're using a 16 color low resolution display. So the bottom 16 colors are exclusive for our sprites. So, first thing we need to do, we need to go grab our SimpleSprite. And like everything else, it's a structure. Struct SimpleSprite, PAC-Sprite. And this SimpleSprite consists of the following information. You can see it over here on the right-hand side in the PDF, the different bits of information that we need to deal with. Okay? So the first thing we need to do is we need to point it to our first frame of our sprite that we're going to use. In this case, it's going to be PAC-MAN right 0, which we still need to define. We'll define right above this SimpleSprite structure. And it has a height of 16 lines. This is 16 lines high. So graphic data. The height. And furthermore, the initial position for this sprite, the X and Y positions for this sprite. And we need to allocate a reserve value for a number. This will be changed by the GetSprite command, but we still need to define it as part of our data structure. This gives us everything that we need that we can pass over to ChangeSprite, that we can pass to MoveSprite to take and alter the sprite that the operating system ultimately gives us. But you'll see that we've got a reference here to PAC-MAN right 0, and that's graphic data. You'll see that that is a pointer to what it calls position control data. Well, what is that exactly? If you actually take a look at what this is, you've got position control, which is two numbers containing that the SimpleSprite stuff is going to change depending on how it needs to position the sprite relative to the copper list of the screen that you're currently on. Okay? And there are also 2 bits of reserved information that you need to initialize to 0, 0 down here at the bottom. So let's go ahead and get these data structures set up here. PAC-MAN right 0. And finally, you need those 2. And our sprite data is going to comprise 16 lines of data right here in the middle. And in point of fact, since these are 16-bit values, we'll try to make this as consistent as we possibly can. And we will have what basically amounts to, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But wait a minute, there are two sets of 16-bit values for our sprites. Yes, recall that sprites are by default 4 colors. Well, you need 2 bit planes for that. So that's 2 16-bit planes of data. And for the case of our sprite data, you'll see right here bitplane 0, bitplane 1, bitplane 0, bitplane 1, and so on, and so on, and so on. That's how it's allocated. They're interleaved together. So if we take that, we go ahead and cut and paste that a little bit. Oops, shoot. I caught something in from the, oops, my bad. That's something from earlier. Excuse me. Try that again, mark set, copy, and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that should be 16 lines of sprite data right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Okay. So we've got 16 lines of sprite data, and our PAC-MAN sprite is going to go right here. Well, PAC-MAN's a single color, so we only need 1 bit plane, but we still have to define both bit planes. This particular section over here is going to be all zeros, but we have to implement it that way anyway. But we have to put the data in here anyway. Now I'm going to show you how the exact process of how I take and draw out PAC-MAN here. We're actually going to take and do this twice. We're going to do this once here for the PAC-MAN sprite, which is a single color bit plane here. And then I'm going to take and extrapolate this in the next video for the ghost blitter object here so that you can see how this is actually done for the other sprites. But that's next video. Anyway, so position control data, bitplane 0, bitplane 1. Now we take and go grab me another terminal window real quick. And I'm going to go into, you're wondering where my graphics resources are coming from. I'm pulling them verbatim from a previous port of PAC-MAN that I did for the mindset. And if we go into our bobs, our blitter objects here, because everything in PAC-MAN world is implemented as a blitter object, you can see that these are graphic data for each of the individual movable characters inside of PAC-MAN, but they're implemented like chunky pixels for a 16 color, that is 4 bits per pixel chunky pixel. So what I'm looking right here is PAC-MAN write 0. PAC-MAN with his mouth completely open. Okay? There are 3 frames to PAC-MAN's animation. This is the first one. And it looks like this. How do we use it? Well, let's take and grab it first and foremost, because I'm going to take this in to Emacs real quick. Yes, I use both VI and Emacs. I'm a bad person. I know. All right. But I'm just going to take and use a temporary space here. And we're going to put this in. Bam. Let's just bing. Thank you very much. Right now, thankfully for us, the color number 1 is yellow. So all we really have to do is smash the bits together to get what we need. Because look at this. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 bytes with 2 nibbles right here. So if I take and get rid of this, then take and get rid of the spaces in between we get our little bitmap here. So suddenly we have everything we need to take and start drawing out our little bits and pieces. So we start drawing out the first bitmap here. There's nothing on the first line, so it's fine. Okay. We start off with 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And then we do it again. All right. 2 more pixels this way, while also stopping here. And again. So we start filling in the gaps right here to make it all look like Pac-Man here. And so on. Finally, we have one, 2, 3, 4. And then the whole process is symmetrical on the other side. And so on. And so on. And so on. And so on, so on. You know. Sorry. You get the idea. Anyway. So you basically fill it out, and for each one, I'm just going to go ahead and pause right here and not have to go through this whole process here, because this is like watching paint dry. Give me just a moment, I'll be right back. Okay, I'm back. I do try to keep the cuts as minimal as possible because I do want you to see the whole process, but I also didn't want you to see paint dry. So I've gone ahead and calculated each value here too as well. So we have a completed Pac-Man right image. The bit for the right bit plane is not used, so all these values are 0. But what I've now gone through is I went through each one of these and opened up a calculator and literally checked it all against the bits. So we have 16 bits, the lower 16 bits right here. We'll just take and start setting them out. 1, 2, 1, 2, 1, 2, 3, 4, 5. So you can see as I set those 5 bits right there, they all come into play, and their hexadecimal value for those bits within that 16-bit field here, because the sprite reads these bytes from left to right. In this case, anyway, big endian here, bam. So we get 7C0. That's our first word right here. We add 2 more bits to that. That becomes 1FC0. And then we add another bit to that. While removing a bit here, that becomes 3F80, and so on, and so on, and so on. You do that until you have completely drawn out the sprite data for that first sprite. Okay? So now that we've got that, we can take and actually continue on. We have just enough to take and display that sprite on the screen. So let's go ahead and start working towards that. We have our sprite, we have our SimpleSprite here, the structure that we're going to use. We're going to come down here after we draw our maze, and we're going to start drawing our sprite. The first thing that we absolutely have to do is that we need to go ahead and grab a sprite. This is done with the GetSprite function, and it has one return value, the sprite that we're going to get, and we pass it our PAC-Sprite structure above, a pointer to our PAC-Sprite structure above, and we can either specify in the second parameter here a specific sprite ID that we want to get, or if we want the operating system to allocate the next available one for us, we can simply say just do -1 and give us the next available one. Okay? Sprite itself is just a simple integer value. We need to take and go ahead and just grab that while we're at it. So int sprite is -1. At this point, if sprite for some reason is less than 0, that is it's -1, then the operating system couldn't give us a sprite, and we can just immediately go to buy. Okay? Otherwise, we need to actually figure out what color registers, what sprite, given the sprite that we have, what color registers it actually gave us. Thankfully for that, the example program that is given here actually gives us a way to do just that. Because we need to take and set those sprite color registers to what we want here. So we'll simply say K is based on our sprite. We AND it with 0, 0, 6. Multiply it by 2 because the sprites are in pairs, and it occupies the bottom 16 colors of our color palette range. And if we have a definite sprite number here, even if it is 0, we'll still get the right color register here in this range. This also means that we need an int k as well. So let's go ahead and put one up here. So that's the start of our color registers. We can literally take and pass that into set RGB4 to set the colors for the colors that we want to use. And in our case, we're just going to be brute force about it. We're going to set the colors for our screen, the viewport on our screen. And remember, K itself is the first color. That's color 0. Color 0 is transparent. It doesn't really matter. So we're just gonna set to yellow. As yellow as we can be, because we want the red component to be full blast, and we want the green component to be full blast. Same thing for the other colors here, so we'll go ahead and just excuse me for a second while I cut and paste this. So, hold on. K1, K2, and K3. We'll just go ahead and set them all to yellow. Why not? We're also going to want an initial X position right here. And once we get a sprite, once we change the sprite, we should be okay. So let's see, K is 0, and we'll go ahead and set X to 0 here too. We'll just kind of set this here and use it right here. Let's see where we're at this particular point in time. We're at the 30-minute mark with our first compile. Okay. Now what's going to happen here, because we grab the sprite and because we're passing in the we're passing in our SimpleSprite, which has been filled in. Recall that we actually set PAC-MAN right 0 as the sprite data to begin with. When we grab the sprite and it reserves it for us, it's going to go ahead and place it on the screen, especially because we've already told the screen ahead of time that we're setting aside DMA for the sprites. It's going to put it for us with the initial frame at our initial position. But we're going to notice something very unique about the situation. At the end of the day, it's going to do the bare minimum to make this happen. And you're going to find something very interesting when we actually get down to running this here. Okay, almost there. Just do the link real quick. Okay, so we've now done it here. Let's run the sprite pack and let's see what actually happens. Now, it's kind of interesting. What I actually need to do here, actually, let me go ahead. I won't feel good unless we actually do this first and foremost, because we'll have to reboot otherwise if we don't do this. We need to recall that we had GetSprite. We need to free our sprite when we're done with it. Otherwise, the operating system will leak that sprite, and it won't. Yeah, anyway. But, all right, let's just go ahead and run it. Now, didn't happen, because nothing happened here, but we'll just let this delay. We'll move the sprite into position. And change this. Let's say move the sprite in position. So let's do this. MoveSprite. Okay. Give me a moment. We want to move it relative to the viewport. PAC-SPRITE. And we want to take, and just for right now, we'll put it right there at X position 64, Y position 64. Because, you know, why the hell not? Okay. Let's go ahead and try that again. I want to take and make double sure here that I did this right. K+1, yeah, yeah, because I saw the mouse pointer change. Now recall that since we actually take and since we share sprites, the mouse pointer and the PAC-MAN sprites share the same color palette registers, which is exactly why when we ran it the first time here, the mouse pointer changed color to yellow. I don't think I need to do a ChangeSprite just yet here too. I can't remember when I first did this. If we do, then I'll just go ahead and add one in for PAC-MAN right 0 if we have to. I don't think we need to at this point though. Let's just see. Because it should have all the data it needs. We do, yes, it makes sense that we need to call MoveSprite at least once. There's our sprite. But notice that that sprite is now sitting on top of the screen, and it's not moving with the screen here. This only happens with successive calls to the sprite command. And because we didn't free it correctly here, it's still kind of stuck there even with that, because we're leaked. We leaked a sprite, so we have to take and reboot. No big deal. Let's just go ahead and reboot. So that's kind of the important thing, why it's absolutely important to take and free your sprites after you're done with them and you don't need them anymore. So come back in here. Okay, we've got our sprite, it's on screen, we're good to go. Now we can move on. Moving the sprite itself is easy enough. All we really have to do is just call MoveSprite. So we called MoveSprite initially for the first bit of this. We can just as easily now. So it's say x is less than, let's say 320. And yes, sprites use low resolution pixel coordinates. They are low resolution size and they use low resolution pixel coordinates. So 320 pixels here. Let's do this. Now we can just basically take and move sprite. Let's go ahead and do that. And to make sure that everything is nice and nifty, we'll use a function called wait top of frame, which will mean that this task that we're currently inside of will take and wait for the screen to do one full refresh of the frame. So this allows you to do proper frame synchronization. The nice thing about waitTOF is that it uses the copper list interrupts to do this, so it's not busy waiting while it's doing this waitTOF. So it's reasonably efficient to use this routine. So we'll take and we'll change the position so the X, okay, looking good, right? We'll do that. Okay, great. Now we'll take and build again. System. GetSprite. And execute make. So I mean, even at this particular point in time, you saw how easy it is to basically get a sprite on the screen, to ask the operating system for a sprite and have it hand it back to you with the pointer so you can deal with it. And you've got functions that can quickly take and move the sprite around and change its animation characteristics. This whole part of the system, this whole part of the gel subsystem is called the SimpleSprite subsystem. And compared to the rest of the gel subsystem, it is simpler to use. And if you don't need any sort of sprite multiplexing, that is, you have less than, you have 8 sprites or less on screen, and you're okay with the palette restrictions and sharing them, etc., then you can use the SimpleSprite subsystem, and it's it works quite nicely. And for our purposes, for the PAC-MAN, it will work quite nicely, as we'll see later. Go ahead, run through the link. Okay, looking good so far. Notice the size of these binaries too. They're teeny tiny because we're using system functions and whatnot. Yeah, these these programs are very small. And we'll see right here, the sprite is moving across the screen, but now because it's using MoveSprite and this MoveSprite is updating the copper list, it is smoothly dealing with the screen transitions and everything else. And so even if I move it across here and move the screen up and down, the sprite will move up and down relative to the screen just nicely and not bleed onto the other screens. That's the other important thing. So let me run that again. We'll see that here, if I take and move the screen, well, never mind. I think it's because there, yeah, never mind. Anyway, so yeah, there we go, bam. Moving across, okay, looking good. So with that, now we can take and add the final bit of this, which is animation. For that, all we really need to do is add calls to ChangeSprite into our loop here. That's all we gotta do. Okay, so we start with ChangeSprite, and we just kind of do the same thing 3 times here. ChangeSprite, and again, ChangeSprite uses a similar calling convention. We need a viewport that we want to render into. We need the sprite here. And we need a pointer to this PAC-MAN data that we want to change into. So first one's going to be PAC-MAN write 0. That's it. That's the call to the ChangeSprite. And in fact, what we're going to do now is I'm going to take that and replicate it 3 times. There's 0, 1, and 2. The data, the same sprite will just use the 3 different graphic images. I don't have to make 3 separate simple sprites. I just need to change the data that gets pointed to. So we'll come down here, fine. That's great, you saw that. And I will now take and bring in the data, the other 2 frames, right here above it. And I will use my already existing example here. That's also on GitHub, remember. We'll just take and visit our other file here. Workspace, PAC-MAN, Sprite Pack, Sprite Pack C. Bam, read the file in. So, PAC-MAN write 1. And I will take, and of course, just like last time here, PAC-MAN write 1. You'll see that the structure is the same. 0, 1, and 2 for all 3 of our animation frames. Pull those in. And if we do our cards right, this should build. As I stated before, in the next video, I'm actually going to be talking about the flip side of this, the blitter objects. And we're actually going to be diving into more aspects of the graphical element system, the GEL system, in order to implement the one blitter object that we need. As it happens, we are going to use SimpleSprites for PAC-MAN himself. We're going to use for PAC-MAN himself, for Inky, for Blinky, Blinky, Pinky, and Inky. PAC-MAN, Blinky, Pinky, and Inky are all going to be sprites. And Clyde, because Clyde's the slow one, Clyde will be the blitter object, the Bob. Makes perfect sense, doesn't it? So, got a link, and with this we should have our reasonably complete demonstration. And we can see Pac-Man just moving across the screen. There we go. Packing along, just packing along. Oop. Uh-oh, we got a halt too. Darn it. What happened to you? I guess there's a leak somewhere, but let's see if we can run that one more time. Wow. I'm guessing I did something very wrong here. Oh, it's because I implemented this a little bit differently than I did in my example. I'm using the same horizontal position for each of those three sprites, but you still got the right idea. I didn't increment the one for each one, so oops. So that's fine. We can just as easily, I guess, take and go back here. I guess we can spend a couple more minutes to take and implement this. Oh boy. Making sure that we take and increment x on each one. X is still less than 320, so we should be okay. Okay, great. Now we take and run system here, go to our CLI. Disk, right back. If you enjoy these videos I'm making, I would very much appreciate a subscription. I'm explicitly turning off ads for these videos because these videos are entirely for learning purposes, and the last thing I want is for you guys to be interrupted by some annoying commercial. I know a number of you have ad blockers, but still, if you're watching this on a mobile device or whatnot that doesn't do ad blockers, then I don't want you guys to be suffering through commercials here. And I hope you guys appreciate that. I get my income from elsewhere, so I don't need income from advertising. Okay, there we go. And then we run Sprite Pack. Yeah, you can see Pac-Man's moving across much faster now. But there you go. There's Packy moving, doing great. So I hope you guys enjoyed this video here. Like I said, the next video is going to focus on building a blitter object using Clyde as the reference, and you'll get to see how multi-bitplane objects are done, how they're implemented, the shadow masks and whatnot, and yeah, it'll be fun. So until next time, guys, have fun.